Okay, this is Unit 10, homework number 4 help. We're going to start with number 1. We've got 0.5 molar hydrochloric acid, and this is a strong acid, so it's going to dissociate completely. 100% of it is going to dissociate. So that means, once again, that we're going to get 0.500 molar H3O plus and 0.500 molar Cl minus. Now, we're not really worried about that at all. It doesn't really do us any good to talk about that, so we're just going to cross it off and erase it, basically. What we are worried about is this guy. We are concerned with the concentration of the hydronium ion because that's going to help us to find the pH. If we find the pH, we're going to use minus the log of the hydronium ion concentration, and in this case that's going to mean minus the log of 0.500. If you punch that in your calculator, you should get then 0.301 with sig figs equals our pH. So that's your answer to number 1. Common mistake on that one is just simply to overthink it. Your answer there should be 0.301 equals our pH. Because it's a strong acid, it's going to completely dissociate. For the second one, I'm going to go to number 3. And this one tells us that we have 5.6 molar hydrocyanic acid. And we've got 5.6 molar HCN. I'm also going to write a balanced equation up here because I think that's going to help us a little bit in our quest to solve this. So we've got HCN, and that's aqueous, plus H2O, which is liquid, going to, or at equilibrium with, Cn minus, which is aqueous, and H3O plus, which is also aqueous. Now remember, I do give you a Ka on this problem, and so you're going to want to use that here. The Ka for hydrocyanic acid, it's on the back of your sheet there in that little table, is 4.9 times 10 to the negative 10th. And we're going to use that in just a second here, but first let's look at some concentrations. Now I'm going to switch colors once more just to kind of keep some stuff straight here. Our concentration of hydrocyanic acid is the 5.6 molar. That's not going to change. Water we're not concerned with because it's a liquid. We don't know the concentrations of the Cn minus or the hydronium ion, so we're going to denote that with an X. Now we can start to plug some stuff in. We know that our Ka is 4.9 times 10 to the negative 10th. We know that the concentration of our reactants on the bottom is 5.6 molar. And we know that the concentration of our products is X and X, or X squared. To solve this, all we need to do is multiply by 5.6 molar. When we take 4.9 times 10 to the negative 10th times 5.6, we should get 2.744 times 10 to the negative 9th, that should be a 9, equals X squared. Now we're almost done here. That 2.744 times 10 to the minus 9 equals X squared. Take the square root of that, and I get 5.24 times 10 to the minus 5th. Now, remember, that number is the concentration of the hydronium ion. Remember what that number means. It's not just an X, it's the concentration of the hydronium ion. That's pretty important for us because now we can use that to find our pH. Remember again that pH equals minus the log of the concentration of the hydronium ion, or in this case 5.24 times 10 to the minus 5th. So when we take minus the log of that answer, we get 4.28 equals our pH. So that should be your answer for number 3, is 4.28 equals the pH. Last one that I'll do with you here is number 4. This is talking about hydrofluoric acid, and it tells us that we have 5.634 molar hydrofluoric acid. The table on the back also tells you that you have that the Ka, for hydrofluoric acid is 6.8 times 10 to the minus 4. Again, I'm going to set up a balanced equation here. We're going to have HFAQ plus H2O, or water, liquid. And there's our little double arrow thing there. And then we've got F, or the fluorine ion, and that's aqueous, plus H3O plus, or hydronium, aqueous. Now that we've got that thing set up, we know that the concentration of our HF, or our hydrofluoric acid, is going to be 5.634. Nothing too crazy there. We know that our water we can ignore. And once again, since we don't know the concentrations of the fluorine ion or the hydronium ion, we're going to denote those with an X. Now again, we're going to plug stuff in. Sorry, I shouldn't have moved that yet. We'll use our Ka, 6.8 times 10 to the minus 4 equals X squared over 5.634 molar. Again, to solve this, we're just going to multiply by 5.634. And when we do that, we should get 0.0038311 is what I get on my calculator. So I'll round that a little bit. 0.00383 equals X squared. And then to finish that off, we'll take the square root of it. And what I get here is 0.0619 equals X. And again, it's pretty important to remember what that X means. It's right there. That's the concentration of the hydronium ion. So that equals the concentration of the hydronium ion. To finish this one off, we'll take minus the log of the concentration of the hydronium ion minus the log of 0.0619. And when we do that, that'll give us our pH. And I get 1.21 equals pH. Hopefully that helps you out with the homework number 4 from Unit 10. I will see you tomorrow.